there is exam or something, only have this kind of anyhow, still, but these topics are smaller, there are not many reactions, hopefully they're fine. We just completed chapter 22 and I've assigned both owl and sap. Some variants and other things, and we are going to make it available. We already made the exams available, just that we didn't send the Excel sheet out to the students because we don't want to everybody know everybody else's scores, but we're going to do that. So we only had two exams. We are going to drop one of the lowest ones. So still there are a lot of points left. You don't have to panic yet. We have two more exams for 200 points. We have finals for 200 points. We have online homework, right? The complete homework is 130 points. Hour plus sapling. One of them is extra credit. And I'm going to make one of the homework, the entire STEM 252 into 100 points homework. That's different than the online homework. That's for 100 points. So normally people get 100 out of 100 on that. That is take home. It's a problem set. But that's a lot of problems to prepare you for the final. So just before the final, I think the other problem set. So students do it when you prepare for the final. Final is 1 point. Finance is cumulative. 251 servers will come back for ACS, 50% of the ACS. So the final exam is 50% ACS and 50% mine. Mine would be as usual. You see pattern that we use, pattern. But the ACS is multiple choice and it's 251 plus 252 and 251 plus 252. So we got to be able to score well in the finals. So you still have about 130 points in your hand after taking the point, right? And we have quizzes, right? We drop one lowest quiz. We take six quizzes and we consider only five for grading. We drop the lowest. So same is true with exams. We drop one of the lowest. So why am I telling you this? If you are concerned whether to drop it or the withdrawal time is what? Before 9, right? Or 8 drop on the class, but that's not going to help you because again you have to put the same efforts. Why don't you put the efforts now and get into the class if you can? For other reasons you want to drop, you want to withdraw it, that's fine. But still have about 600 points, 640 points in your hands, so you should be able to do well. So then we just completed chapter 22, and we're going to do it, we're going to discuss chapter 23rd. But I'm covering these two chapters together because the underlying principles are one and the same. The things here is the alpha carbon, just that they divided into two chapters in the textbook. Some of the coverages and some of the activities are listed here. So what does chapter 23 deal with? Chapter 23 deals with more enolate. You know already how to generate the enolate, what is an enolate, what is an enol, why does exist in the tautomeric form, enol form, all sorts of things because of the pK values of the alpha hydrogen, whose acidity differs depending upon the types of carbonyls that you have. Ketones have different pK, aldehydes have different pK, bicarbonyl compounds have different keto form, keto form. So fourth, we also talked about acetoacetic chemistry and chemical validate chemistry. There is two carbon compounds, two carbon plants, one methylene is plant with two carbon compounds. He said that these enolates react with electrophiles and they act as nucleophiles and we form a new bond. So the electrophile would be change the electrophile now. What about using other carbonyl group itself as an electrophile? We talked about the carbonyl groups are electrophiles of that carbon, the nucleophiles of that carbon. Can we have self-condensation, self-reaction? We're taking carbonyl compounds and we are going to use the carbonyl compounds as electrophiles and we make them react with each other. For example, the carbonyl compound here. We are taking the alpha proton, generating an anion, adding to another carbonyl group. So these are called Aldol reactions. Not over the condensation reaction. But the chemistry is happening between the carbonyl compounds. I have a carbonyl compound as electron donor, I have a carbonyl compound as electron acceptor, and have that relation of we will combine two of these molecules for similar coordinated in both the cases are to be the little piece of compound here, so the compound depending upon the okay, that's understood that and take two more of the formula. One more of the have one more of something. Good action. Right? The one you generate usually that's carbon reactor and acceptor. You make a new bond. That's carbon-carbon bond. Carbon-carbon bond formation is very important in organic synthesis, right? So this is reactions are called Aldol reactions. Let's take this propionaldehyde. There are two modes of it. One mode of it is employed, negative phase. So you make it innovator out of one mode, and the other one has an acceptor. That is the alpha proton. It's not alpha proton. Alpha proton are those which are attached to alpha carbon. Alpha carbons are next door carbon. You have to leave this carbon carbon. Look at the next door. That's where the alpha atom is. That's the space of the proton. That ion is generated and added to this carbon. Carbon can be written in this resonance form. The electrons are dropped and after the computer form. That's why the carbon is electrophilic. The carbon is electron form two bond and we generated an ion. And during the workup it picks up the proton, so you add some water and you get the proton. So you have a carbon group and an alcohol, so it's called Aldol reaction. So what are the acceptor and we have it right? That's condensation. The two modes of the same molecule. Because you still have aldehyde and alcohol, or you still have a carbonyl and alcohol. So you call it, so you could call this an Aldol reaction. And these are reversible reactions. What we use is double-headed acid. What do I mean by that? If I have a base, if I have an Aldol product, if I don't have any water, I can pick up the proton and then break this bond. In a pure fashion, I can go back. That's called Aldol reaction mechanism. I have a base that can pick up a proton. These are atoms that push backward into the space. So this bond breaks, and as a result, we generate uranium, that, which way is stable, depending upon what you're eating it. We have a set of ways, which point of this is right? So, you got to be careful when you do all our reactions. Not to have once they use the instruction, such that I want to break this carbon bond, I can do it to all of it. Right? So what's common for the outdoor reaction? Both the outdoor reaction, the base is common. Except in the former case, the base is um, to pick up the alpha proton. In the latter case, we are using that as base to pick up the hydroxy. So here I have 1, 2, 3, 4 glucanone, and and use that as a two more cognitive condensation. One mode is converted to an anion, another mode is still active as an acceptor. So not only we are looking at the alpha carbon, also we are looking at the carbon itself. So whatever we learned in chapter 19, chapter 20, chapter 21, as well as this reaction, we are in chapter. That's the reason we are talking. So alpha carbon is involved, but the carbon is also involved. All our reactions involved out of self-condensation. What are the bases that I can use? I can use sodium hydroxide, or I can use potassium specific oxide, or here, so it's not a nucleophile. Base is a nucleophile. It would not attack the carbon. So you can increase the specificity. Well, carbon don't want it to act as a nucleophile, you don't want it to attack the carbonyl, so you increase the bulkiness. So these are non-nucleophile. Hydroxide also is a nucleophile than a base, than a nucleophile. Sodium iodide, potassium iodide, sodium oxide, all you can just remember some of those reactions. Okay, so this is another reaction which is starting that have excess of base and we keep this reaction. It doesn't stop at just all alcohol stage. The excess of base will come back because we keep it acting as a base again, and the pieces of this alpha proton of the product. First step is picking up the alpha proton and adding it to itself to get the alpha. But because we're going to keep it and we have an excess of base, we pick up the proton of the product and the alpha and also is taking off. So as a result, we eliminate the molecule of water. Whenever we eliminate a small molecule or a big molecule, we call the reaction condensation or condensation through water by eliminating the small molecule. This is elimination by itself here. But if you look from here, what are you doing? You are taking two molecules of your carbonyl compound, condensing them into one by eliminating the molecule of water. So these are called condensation. Just look for the Aldol reaction. We use the word called condensation reaction. What is the key is that control your reaction temperature to base switches and the excess of base temperature leads to elimination, and the elimination is not happening in any other direction. Elimination is happening in such a way that the double bond is in conjugation with the bond. The phase is not taking the protons from here. It's not eliminating the double bond. That is not in conjugation with the carbon. Why is it not taking from here? Because that is not as acidic as alpha hydrogen is. Right? That's common. Whenever you have a base, it will only take those protons that are acidic. Only protons that are acidic in this compound are there is hydroxide proton. The hydroxide proton, if you fix the hydroxide proton, is under black hole. That's called the alpha proton. This reaction is not reversed. Any questions about it? If not, the whole Aldol condensation is shown here. Two moles of your starting material, you generate the unit, you add it to the file, that is the result. The condensation unit, got an Aldol product out of it, Aldol product further undergoes dehydration. You can isolate at this stage, and then again alcohol undergoes from base. So that's the alcohol. Just as this molecule has alcohol group, so if you want to go all the way from here to here, just start with stronger base and higher temperature. Start with that. But acid and catalyst. So acid catalyst all of acid catalyst reaction doesn't stop at all. Don't stop at all. You can tune the base and then stop it. Use an acid, it does catalyze all the reaction. Condensation process. How does it happen? So now in acid, so you know what acid medium. This activates acid donates the proton and deprotonated, you get oxonium ion, and then you still have water, excess of water for the alpha proton. Now the water can act as a base because this is activated. The electrons are put to this. Otherwise, water would not be able to keep the protons of this compound. Because you have acid, water is compound. So it picks up the alpha proton and now you can let enol. You don't call it enolate because there is no charge. The enol form, enol is also a good nucleophile. So you have an electrophile. Now the electrophile is activated. Same species that you generated here, protonated, because acid protonation all equal to the top of it, top of acid, protonated form that was reprotonated and converted into enol. The enol acts as a nucleus file and it has the electron file and the electrons are good. And there is a one formation. The electrons from here to that carbon, that forms a bond. When you have a powder, if there is no bond, that means you are making a new bond. So already have a bond, you are breaking it. So you are forming a new bond between that carbon and the alpha carbon. That's alpha carbon. So you got Aldol product. But here we have some extra protons from one of them, and that is intramolecular proton transfer. Protonated species, just as the molecule is strong. So this problem is this one. Just as we saw in protonation, we have protonation, some intramolecular proton transfer at some stages. Water is active. Notice that in all these mechanisms, either we have neutral molecules or we have positive. We don't have negative charge because we are an acid means. Acid means full of protons. So when you write your mechanism, acid means protons or neutral. Electrons or okay? So this is how of all of the condensation using either acid or base. Summary of all of the actions happen. And the acid medium cannot stop. Because acids easily protonate alcohols. Alcohols become good leading to heat, and the carbocation is formed. Heat. It could be even mechanism or any mechanism. Nobody knows those things. The basic medium. So here you go. So this is an all-out reaction of cyclohexanone. Base is picking up the alpha proton. That's the alpha carbon. The base is picking up the proton, and that's generated phenolate. And the same molecule is acting as an acceptor. The electrons are moved to the carbonyl, and the hydroxy group is formed after protonation. So you get to Aldol product. And if you have heat, if you heat the reaction, or if you have acid as extra base, we generate the output and heat the anion. So this is called dehydration. Dehydration is an elimination reaction has two classes, either easy or E2, depending upon whether you have primary alcohols or secondary alcohols or tertiary alcohols. Tertiary alcohols and secondary alcohols under the E1 mechanism, primary alcohols under the E2 mechanism. But at the end of the day, what is the product? Now, P is the product out of elimination reaction. Okay. So there are three ways to do this reaction. First, we start off with dilute base, controlled amount of base, and then you heat it. Or you start off with stronger base and heat. don't see Aldol product, but you see directly eliminated product. Or you start off with acid. You don't see pay attention to what is in the arrow, right? So this summarizes the whole discussion of three different ways to do the Aldol reaction. First step, you just want to stop at Aldol product, so you don't quite heat it. You use dilute amounts of base. Okay? If you heat it, you need to heat. Or if you want to make coffee, okay? And when elimination happens, let's say you have hydroxy group in the product here, right? This is being eliminated as a water molecule. Let's say this leaves. As a result, you get, I'm writing an even mechanism. Carbocation is formed first, and then the proton is created. So this carbocation has two choices. This hydrogen could go, or this hydrogen could go. As a result, the double bond could form here, or the double bond could form in this direction. But the double bond always goes alpha to the carbonyl. That means it's always conjugated double bond. You don't get non-conjugated double bond. Now, what is the non-conjugated double bond here? The non-conjugated double bond could have been something like this, because this carbocation could have gone with this carbon, and that could have formed a double bond like this, but that's not stabilized. Stabilized double bond is gone. Why is this way again? Because this alpha hydrogen is more acidic than this alpha hydrogen. So base has two choices to keep the proton. The base will keep this proton. That is adjacent to the carbon. This is not adjacent to carbon. So, got to remember that. Although reaction happens, the water eliminates, but elimination happens. So you make alpha beta unsaturated orbital alpha beta. Okay? You don't make this gamma. Okay, so that's comparison of what we learned in chapter 21 and chapter 20, sorry, 22 and 23. In chapter 22, we used alkylation as a reaction, where we used alkyl halides to react with enolates. In this chapter, we are using carbonyl itself is as an electrophile. We are making enolates in both the chapters, in both the reactions. The enolate is now added to electrophile. Electrophile is the one that accepts electrons. This carbon is electrophilic because the electrons are polarized because of iodine. So the carbon is electrophilic delta positive. This carbon is delta positive because of this polarization of the electrons. Right? So you get all the reactions. So you do make carbon-carbon bonds, but you still have some more functionalities. You hydroxides to do something else, right? You can use these reactions for making other reactions. So let's say you want to do alkylation, and let's say you use a weak, whenever you have a weak base, you generate an anion, but the equilibrium is in play. Not only make units, so they would find each other. Though you want to do alkylation, alkylation doesn't work. Not only you make this product, but also you make this product. Why is that so? Because you're using heat. You're not completely converting all of it into an anion. If this was supposed to be this way, one direction, you would only have anion, and the anion would only react with electrophile, and you would have got this product. As you can see here, when you have a stronger base, you completely convert. It doesn't have cleaner reaction. If you use a mild base, not only do you see alterations that you want to do, but also you will right? So, Aldol reaction, mild base is fine. If you want to do an alkylation, you rather want to do. And now, this probably is not happening itself. So, and I can do cross condensation. So I don't want to condense with itself, but I want to do an Aldol reaction with a different aldehyde or ketone, then I can add a different aldehyde. So then I can see cross Aldol condensation reaction. So this is the synthesis problems. We learned the Aldol condensation and Aldol reaction. Then you design a synthesis for these compounds. You just have to identify the alpha carbon as an anion, break the bond, and then this is a co-synthesis of this. This side has to be an aldehyde, that's what becomes the reactive group. And we are breaking this bond, and that has to be an anion. So you can plan the reaction from there. How do I generate an anion? Once I make the hydroxy compound, I can go backwards. I can go dehydration. Right? So you can plan the synthesis. It's like Grignard reactions. You learn the Grignard reaction, so now you can do Grignard reactions, right? Either on the paper or in the lab. So the same way all our reactions is also a carbon-carbon bond. But Cannizzaro is not an Aldol reaction. This is a Cannizzaro reaction. What is the condition for Aldol reaction? Aldol condensation need anion, right? Alpha anion. So at least there should be one alpha hydrogen in the carbon. If I don't have alpha hydrogens, let's say I have a ketone like this, I cannot do an Aldol reaction of the compound because I don't have alpha hydrogen. I cannot make an enolate of it. No hydrogen, no hydrogen. So what's the criteria for Aldol reaction? At least one of the parties, of the two parties, you have two parties. Right? One is lower and one is higher. There should be one alpha hydrogen. Mechanical reaction, right? We don't have alpha hydrogen. This is our carbonyl group. The alpha carbon is sp2 carbon, and there is no hydrogen. If you are not seeing that clearly, you can write like this and see that there is no hydrogen there. 4 bonds to carbon. 1, 2, 3, 4. Okay. So aromatic aldehydes do not participate in cell translation. So Cannizzaro reaction is a bit concentrated sodium hydroxide, but it doesn't undergo Aldol reaction, it undergoes a redox reaction. That redox reaction is just one mole of aldehyde undergoes reduction, one mole undergoes oxidation. So net is right? So it's a redox reaction. Half the molecule undergoes, half the equivalent, half a mole of the aldehyde. So you get alcohol, lower oxidation level than what we started with. Aldehyde is in the middle. Alcohol is one lower level of oxidation. One more goes that direction, but half a more goes in this direction, half a more goes in this direction. And we already saw the mechanism in the last chapter 19 or so. So I'm not going to go into the details. But that is that. So Cannizzaro reaction is not an Aldol condensation. So if you want to reduce the aldehyde, you don't use the sodium. Just use Cannizzaro. Just add form one. So anyhow, that's that. But let's say I do uniform one. So one of the partners has an alpha. That can act. Another one does not have an alpha hydrogen, but this can act as an donor receptor by choosing two partners such that only one of them can act. Any questions about that? Let's look into cross-Aldol reactions. These are examples of cross-Aldol reactions, where one of your starting material is acting as a donor that is picked up. The base picks up that proton is acting as a donor, acceptor. So this is your donor, acceptor, and that's the new carbon-carbon bond formed between those two. Okay? So the bond is between the alpha carbon, that's your alpha carbon, and the carbonyl carbon of the other species, that's the carbonyl carbon, and that's your alpha carbon, and that's the new carbon-carbon bond. And you made an aldol product, and if you want to heat it, it undergoes elimination to give alpha become saturated ketones. These are called cross aldol condensation, because now you are doing aldol condensation between two different molecules, not just condensation, right? And this is also cross aldol condensation. You do see three products, just that this might be major, right? So that's the complication of aldol reaction. Whenever you have two partners, two different partners, for example, I have an acetaldehyde. That's the hydrogen. If you cannot see that, you can write down. This also gets converted into donor. This also gets converted into donor, that is enolate formation. So you have two enolates and two acceptors. This is an acceptor. So how many products are possible? Altogether we have four products, because you have two donors, two acceptors. You can make two different enolates, and all of a sudden you have four partners, or four of them can react. Various ratios. So let's say so sometimes the synthetic utility of this reaction goes down because of this complication. How do I do this more effectively? If I have to get this reaction to be any synthetic utility, then I have to make sure this. I make sure that there is only one of the two carbonyl compounds that can undergo enolization, one of them does not have alpha. Then I am directing the reaction starts with the side, right? And they will do cross condensation. One of them only act as a drone. This can increase the synthetic utility of this reaction. Another way, I make sure that I use a strong base so that all of my donors are. So this is where I make sure there is only one of them that has alpha hydrogen. Formaldehyde, benzaldehyde, they can only act as acceptors. They cannot act as donors because they don't have alpha hydrogen, right? So there's only one product that I can see. That's the product. And here I'm using benzaldehyde. So these are cross condensation reactions where only one of them is immunizable, but one is not immunizable. Green one is not immunizable. It's only acceptable. Strong base. So I convert all of it to donors. That's my acceptor. And then I can get all alpha. So the dark bond over here. This is another Aldol reaction where one of them is donor and the other one is the acceptor. Only acceptor can act as, not act as a donor. So I get Aldol. Or I got to make sure that I use a strong base like LDA. If I use LDA, now I add my second species. As a result, I can put this reaction the way I want and I can get the product. No more form. So I add the second element for after the generation of the universe. And then this can only act as an acceptor. Then I can make this reaction synthetically useful reaction. Okay? But again, you have this kind of as a result, I can make two units. So I also need to control the temperature. If I don't do it at the minus temperature, I generate two units, right? This is kinetic inlet where this left hindered proton is picked by the base. So you make an ion only on the left hindered side. What is the other inlet that I can make? If I pick this proton, I can make the other inlet, and that even if I use LDA at a higher temperature, like say room temperature, since I have two units, both of them can act as donors, though I am only adding this on. Temperature of the reaction. Get minus temperature. Permanent product. If you want this mixture of products, you accumulates, and as a result, you get to move that to product. Any questions about Aldol condensation? So if not, let's look into how to solve some of the problems. Let's say I will give you something like this, you're doing something like this, and you're asked to identify. So I can cut this, and then I can write this reaction. So this is acting as a donor. This is a new carbon-carbon bond. So always cut the bond that is adjacent to hydroxy. That's where the carbonyl would have been. That's where the addition has taken. Is there any other way I can do this reaction? then oxidize that. So I'm not doing any oxidations and reductions here. Do I have an alcohol? In a reducing agent for oxidation, you're only using inolates. Accept this. Right? Just that we are not using inolates. So in the synthetic reduction, this is how we do that. You don't want to you're not heating it, you're doing you want elimination, then you take this one. And alkene, make sure that aldehyde any questions? So it's important in synthesis because it can be used to make hydroxy compounds. So those hydroxy compounds are normally beta hydroxy compounds. I cannot make alpha hydroxy compounds out of this reaction. I cannot make something like that. That's alpha hydroxy. What is Aldol product? Aldol product is always beta hydroxy. That means one carbon away from the carbon. Carbon is carbon, alpha is not. So the beta hydroxy compound can be made from Aldol, or they can be subjected to the two Aldol. Right? Also, I can make alpha beta. From the beta hydroxy compound, I can do one elimination. And then that becomes a Michael acceptor. That becomes alpha beta unsaturated compound. And I can add nucleophile to this. Right? Because here you go. So what is the synthetic utility of all our products? You can reduce the carbonyl that you have in all our products. Right? So all of a sudden you have two alcohol containing groups. You can eliminate, you can make aldehyde, alpha beta unsaturated compounds, and you can saturate them without right? Or you just reduce this carbonyl group now. Or you can do complete saturation. You can do control reduction by force it to undergo. Or ketones. Can we do this intramolecular? What if you have a donor and acceptor within the molecule? I have two carbonyls within the molecule. One side I generate an anion, I add to the same molecule on the other side. So I can make the hydroxy compound like this, and I can do the elimination. I can make cyclic ketones. I can also make unsaturated ketones. But when you have intramolecular reaction, the ring size matters. You don't make more, so we don't pick up this alpha hydrogen and don't add to this carbonyl because we're supposing that we're making three carbon ring, so that does not happen. Though there is nothing wrong chemistry-wise, we're doing everything correct. We're picking the alpha proton, but just that you're picking a wrong alpha proton. It has many alpha protons, right? That's alpha proton, that's alpha proton, that's alpha proton, that's alpha proton. It's symmetrical, so this is same as that, this is same as that. So either you pick this anion or that anion, right? So this anion would give 7-member ring. So you are picking up this proton, this anion, and then adding to this carbon. That would be a 4-member ring. So you have to pick this anion and add to this carbon. So 6-member ring. So the order is 5-member ring, 6-member ring, 7-member ring, then 4-member ring, and 3-member ring. That's how the order goes. So the easy to make one, although we have 5 carbons, 6 carbons, 7 carbons, and then 4 and 3 because they are very highly strained because of the ring strain. If I have something like this, I can do an intramolecular reaction out of it, intramolecular Aldol reaction, Aldol condensation, and then I can make as a product. For example, this is a star. Now, that you go like this, Aldol condensation, and you can make that ring out of it. That's where the Aldol reaction happens. Right? So if I have something like this, I can make this by word analysis. With that, I'll let you go. Next time we'll talk about